Okay, now we are going to see some more formulas of dimension of various different physical quantities. So we have already seen some of the physical quantities dimensions. So now we are going to move on a better on the part where dimensional formulas become a little bit complicated. Not exactly complicated, but a little bit considered to be tough side. Okay, so those dimensions now we are going to see how would we derive the dimensional formula and questions based on them. Okay, so let's see first. We have Planck's constant. Planck's constant. So these are the formulas that you have to be very quick while solving, because the question would be based on not exactly that, not directly they would ask the dimensional formula, but based on these dimensional formulas they would need some more quantities. Okay, some questions would be there which would be involving these type of quantities. So you should know how to calculate the dimensional formula of these quantities quickly, so that you can write down the dimensional formula or you can solve the question further. So if you remember Joule's constant, Planck's constant, its unit is how much? Joule second. So dimensional formula of Planck's constant, Joule second. Joule is energy. We have done already ml2 t minus 2. Second is time. So it would become ml2 t minus 1. That is Planck's constant. Okay. Easy to derive. Next one. Gravitational constant G. So force equals to gm square by r square. We need the dimensional formula of universal gravitational constant. So here universal gravitational constant, we can write that capital G equals to force into distance square upon meter square, force mlt minus 2 L square, mass kilogram square, sorry, capital M square that also. So it is m minus 1 L3 P minus, clear. Universal gravitational constant also clear. Okay, next one, specific heats. So Q equals to ms delta T. This formula is for solids, liquids, and that formula for gas in terms of mole it would be Nc delta T, right? So here S is a specific heat, so Q upon m delta T. So if you write down the specific heat capacity dimension, so joule energy ml2 T minus 2, mass m, temperature K. So it would become L2 T minus 2 K minus 1. Okay, heat capacity here, joule. Q is heat. Heat is an energy. Energy unit is joule. So ml2 T minus 2. Mole we can leave is that unitless, delta T K. So ml2 ml minus 2 T minus 2 K minus 1. Sometime mole inverse also you can write if it is given in the option, otherwise not required. Okay. Now, okay. Next dimension, PV equals to nRT, universal gas constant here, and PV equals to n Boltzmann constant temperature. R is called universal gas constant. So if you want R, you will write down PV by T, PV by NT. So PV is nothing but energy. So ml2 T minus 2 upon mole, leave it T K. So ml2 T minus 2 K minus 1. Clear? Similarly, if you talk about Boltzmann constant, so Boltzmann constant is also PV by NT. N is number, so no need to write down there is no dimension for this one. So it would come out to be same. ml2 T minus 2 K minus 1. So Boltzmann constant, this is very important. Multiple times this one has been asked. Boltzmann constant and universal gas constant. Both has same dimension. How much? ml2t minus 2k minus 1. Okay. Force equals to 1 upon 4 pi epsilon naught q square by r square. Coulomb's law. So if you talk about epsilon naught, so epsilon naught would be q square upon fr square dimensionally. 4 pi is a dimensionless constant, so I'll leave that. Okay. So charge is at, so a square t square. Force mlt minus 2 r square is l square. So it would become m minus 1 l minus 3 t4 a square. This is the dimensional formula of permittivity of free space. M minus 1 L minus 3 T4 A square. Again, you do not need to remember all of these things. If you are able to connect it quickly, that would be okay. Okay, from here we have one few more relations that we can connect with permittivity. If you talk about speed of light, c in vacuum, it is given by 1 upon root over mu naught epsilon naught. Okay, important relation. Speed of light in vacuum is given by 1 upon root over mu naught epsilon naught, permittivity of free space, permeability of free space. So squaring both sides and calculating the value of E naught, it would become 1 upon c square mu naught, or mu naught basically we need. So mu naught is 1 upon epsilon naught c square. Okay, squaring both sides, right? Yes. So if you talk about mu naught, it is 1 over epsilon naught. So 1 over epsilon naught would be how much? M L3 T minus 4 A minus 2, reciprocal of that, divided by C square. C is LT minus 1, so L2 T minus 2. So it would become M L T minus 2 A minus 2. So permeability also clear, right? So epsilon नॉट हमने देख लिया है, म्यू नॉट हमने देख लिया है. So next one हम कर सकते हैं field. So if you talk about electric field is given as force per unit charge. Force mlt minus 2, charge at. So it would become mlt minus 3 a minus 1. That is the dimensional formula of electric field. Okay. Now, a question they would ask, no? So question they would ask something like this: half epsilon naught E square, or it can be asked B square by 2 mu naught. Now in this case you will find out that E also you have to derive, because you would not remember epsilon also you have to derive. Similarly B square, B also you have to derive, mu naught also you have to derive. So that much would become a little bit time taking, consuming process. Okay, but simply you have to remember this half epsilon naught E square. It is what? It is called energy density. Both are what? Same. Energy density. This is electrical energy density, magnetic energy density. So energy density is nothing but energy per unit of volume, and we are familiar with energy, ml2 t minus 2, volume L3. So it would become how much? ml minus 1 t minus 2. So overall this one you can remember this. Okay, half epsilon naught E square, B square by 2 mu naught, it is energy per unit volume. So ml minus 1 t minus 2. If you remember radiation chapter, so there is a constant called, if you talk about rate of heat flow, so sigma a t power 4, Stephen-Boltzmann constant, Stephens-Boltzmann law. So this sigma is called Stephens constant or Stephens-Boltzmann constant. So Stephen constant Q upon a t power 4. Q is basically Q dot, means rate of heat, that is watt. What is what? Watt. So area meter square, temperature power 4. So watt is nothing but joule per second. So we can write ml2 t minus 2, joule per second t, L square. This is temperature. So K power 4. So sigma would become how much? L cancel, L cancel. Mt minus 3 K minus 4. Okay. Mt minus 3 K minus 4. Stephen Boltzmann constant. One more constant we have, Rydberg constant. Rydberg constant. Rydberg constant. It is nothing but meter inverse. Meter inverse means L minus 1. Rydberg constant. One more we have Reynolds number. Reynolds number. Reynolds number is a pure number that decides the flow of a liquid whether it is laminar or turbulent. So Reynolds number is dimensionless basically. M0, L0, T0. Okay. अगला देखते हैं सरफेस टेंशन. Surface tension. So surface tension S is nothing but force per unit length. So force mlt minus 2 per unit length. So L. So it is mt minus 2. That is surface tension. Next one is spring constant. So spring constant. So Hooke's law, F equals to kx. So k is the spring constant. That is also force per unit length. So it would be mt minus 2. So these two are same. Surface tension, spring constant. Okay. Next one we have Stokes law. F equals to 6 pi eta rv. This is Stokes law. Here eta is called coefficient of viscosity. So coefficient of viscosity would be given by x of f upon rv, radius velocity. Here 6 pi is constant, so no need to write it dimensionally. So force mlt minus 2, radius L, velocity lt minus 1. So ml minus 1, t minus 1. So that is dimensional formula of coefficient of viscosity, ml minus 1, t minus 1. Okay. Next one we have thermal conductivity. So if you talk about rate of heat flow equals to Ka dt by dx, temperature gradient. All these equations we will see in their respective chapters. So again joule per second, K is called thermal conductivity. So K equals to joule per second, so Q by T. A would be divided here, dx is length, dt is temperature. So joule ml2 t minus 2 upon time t, area L square, dx here is length and temperature here is Kelvin. This is thermal conductivity. So thermal conductivity would become m L t minus 3 K minus 1, thermal conductivity. Okay. Let's see next one, electric potential. So potential is given as potential energy per unit charge, again energy. So ml2 t minus 2 per unit charge at. So ml2 t minus 3 a minus 1. This is electric potential. If you talk about gravitational potential, so gravitational potential would be given by potential energy per unit mass. Potential energy again ml2 t minus 2. Energy of every type has the same mass, so upon mass, so L2 t minus 2. Okay. Okay, now so if we have got this electric potential, we can connect a lot of things from here now. Electric potential. Okay, so we have voltage formula here, dimensional formula of electric voltage. So we can connect here V equals to IR. So from there resistance would be V by I. So ML2 T minus 3 A minus 1 upon I is A. So it would become ML2 T minus 3 A minus 2. Okay. Again from here only we can connect Q equals to CV. So capacitance formula would become charge AT upon voltage ML2 T minus 3 A minus 1. So it is M minus 1 L minus 2 T4 A minus A2. If you observe this R and C, so RC would be how much? M minus 1, L2 minus 2, A minus 2, A plus 2, T minus 2 here, T4 here. Okay, T minus 3 and T4. So how much would remain? T. So RC is nothing but what? Time. That's why RC is also time constant. Okay, next one. We need magnetic field. So force is given by QVB. So from there magnetic field would be force by QV. Force MLT minus 2, charge AT, velocity LT minus 1. So M A minus 1 T minus 2. This is the dimensional formula of magnetic field. Ma minus 1 T minus 2. Okay. One more formula we have here. If you talk about mutual EMF is L di by dt. So EMF we just saw. What was the formula of voltage here? That is resistance. Where is it? Oh, here. So EMF is how much? ML2 T minus 3 A minus 1. So ML2 T minus 3 A minus 1. Okay. L di current is ampere, T is time. So here L would become how much? ML2 T minus 2 A minus 2. This is inductance. ML2 T minus 2 A minus 2. Okay. Now from inductance we can connect flux also. So flux equals to Li. Flux would be Li. So ML2 T minus 2 A minus 2 into current A. So it would become ML2 T minus 2 A minus 1. This is magnetic flux, not electric flux. Okay, magnetic flux. Okay, so you can write down the electric flux also. Electric field into area. Okay. So force MLT minus 2 L square charge AT. So it would become ML3 T minus 3 A minus 1. So this is our electric flux. Okay. So these were the important dimensional formulas that were a little bit tough to calculate. But we saw that if we remember any formula, we can connect them, and interconnection is very important because the questions on dimensions would not be asked like simple one-liner questions. Okay, they would try to connect a lot of complex dimensions also, Stephens, Boltzmann and all that, thermal conductivity, that they would try to connect here and there. So you should be able to do it. Now we have to practice questions on dimensions. So we'll be working on that.